Good morning. Assalamu alaikum to everyone. Today is the 14th August and it's the 70th Independence Day of Pakistan. You can see the flag here. We are, as a nation, celebrating this Independence Day on the and it is special because last months back, a war against India give us proof that at least we can face an enemy. So, today I shall discuss basics of magnetron, and I shall try my level best to discuss the basic physics, maybe excluding the equation. But whenever some equation is needed, it can be discussed. Okay, outline of this talk is introduction. How looks how magnetron looks when there is no RF. That is physics. Type of magnetrons, very basic initial designs of the magnetron, cyclotron frequency magnetron, negative resistance magnetron, then the traveling wave magnetrons. Potential energy is converted into the RF energy in the magnetrons. How can the RF circuit of the magnetrons be explained? How modes are existed? What are their demerits? We can deal with those demerits. And then coaxial type magnetrons. Again, there is another form of magnetrons, inverted magnetrons, how we can tune the magnetrons, how we can and output coupler. Then we shall discuss the performance of the IV characteristics, frequency pushing, frequency pulling. Actually, it is pushing and pulling. Sorry for that. In an article by J.J. Coupling concerning the magnetrons, the following opening statement appeared. The two most important weapons of recent war were the atomic bomb and radar. And it was the magnetron that made the Allied radars incompatibly superior to the Nazi boats. So magnetron was very important, played an important role in the World War. And it is also playing very important role in the economy and in the defense, even in this era as well. So why we need a magnetron compared to the other RF sources? There are a few merits. It's a compact RF source, and it is used in the devices which are movable, portable, for example, portable trucks. And second is where the quality of RF output is not very important. You don't need very precise bandwidth of RF field. You can use it. Its price is low price RF source, and its efficiency is quite good, over 60%. The limitations are amplitude and phase stability. We shall discuss this in detail, because whenever a pulse is generated from the magnetron, it has every time a random phase. Secondly, we have its low average power. Even you can get the magnetrons of up to 7.5 or 10 megawatt, but their average power is very low. And of course, I have already explained, it has a wideband spectrum. Pulse time is little higher, rise time is higher. And for higher frequencies, it is very difficult to fabricate a magnetron. Introduction of the magnetron. Magnetron is a device which can generate high RF power in general without RF input. You need not to feed it an RF to amplify it. It is a device which is operated without RF input, without RF CD. The magnetron, in magnetron, the general motion of electron beam is perpendicular to the both fields, which are mutually perpendicular. You can see here, electric field is, electron beam is moving in this direction. Electric field showing by red arrow is in this direction, and magnetic field is outward or inward of this slide. While in other amplifiers, fields are almost in the same direction or in the same line. At least two are in the same line. If there is no RF in the magnetron, then it is called pulse magnetron. The first magnetron was invented by A.W. Hull in 1921. It was not an RF device and was used as switch tube that could be used to control the current. Here you can see 3D of a magnetron. This is a cathode. Inside it is a heater which heats, electrons are emitted, and there is an anode outside, which is at very high potential. So emitted electrons, here is the coupling. RF generated inside is coupled to the output, is coupled to the outward circuit. When there is no magnetic field, what happens? An electron emitted from this surface moves towards the anode. And initially, its energy is few electron volts. It gave the energy and hit to the anode. When it hit to the anode, its energy is voltage applied across the anode and cathode into its charge, EVA. Now, when a magnetic field is applied, these electrons under the influence of magnetic field move in this direction. Now, there are two scenarios. If your magnetic field is very strong, this emitted electron, this emitted electron will spiral back to the cathode, hit back it, and will produce heat. And if it is weak for a fixed anode potential, it will hit to the anode. Similarly, if we have a fixed magnetic field and vary the potential of cathode, same scenario happens. For small potential, electron will hit back to the cathode, and for higher potential, it will hit to the anode. Now there is a critical value of anode voltage, which is called VH. If anode voltage is higher than that critical value, the electron strikes back. If it is less than that critical value, electron strikes to the anode. Similarly, there is a critical value of magnetic field. If you fix the voltage by increasing the magnetic field from the critical value, cause the electron to hit back to the cathode and if it is smaller than that critical value, it hit to the anode, and there is a very critical value where the electron just touches the surface and come back to the cathode. This is called the critical magnetic field, and this critical magnetic field is called Cole's cutoff condition. All the magnetrons except a few one we will discuss in the next slides are operated in the condition that the voltage is less than the Cole's cutoff condition. So here is a graph. You increase the magnetic field, operation region of normal magnetron is increasing. Cutoff parabola or cutoff condition is increased, that you can apply more anode voltage to the magnetron. There are three types of magnetrons. One is first one is very initial stage of the magnetrons when these magnetrons were developed, cyclotron frequency magnetron. Second one is negative resistance magnetron, and third one is traveling wave magnetron. The first two are not longer in use, but understanding their physics will help us to understand the basic phenomena or physics of traveling wave magnetron. The first two are operated very close to the Cole cutoff condition. Their operation voltages or anode voltages are very close to this cutoff parabola. The traveling wave magnetron operate at voltage and magnetic field that are well below the Cole cutoff parabola and are very efficient. The presence of RF current, the high efficiency of these devices results from a very efficient conversion of power energy to RF energy as the electron move from the cathode to anode. Now, first of all, we discuss cyclotron frequency magnetrons. As I told that it is operated very close to the cutoff frequency of Cole's cutoff frequency condition. There is a resonant circuit is attached to this magnetron, and those electrons which are moving here and comes here at the region 1, they contribute to the resonant circuit. They induce RF in the resonant circuit, and at this region again they contribute the RF to the resonant circuits. In all these magnetrons, cathodes and anodes are coaxial, are cylindrical and concentric cylindricals. This cyclotronic, this electron which is performing a cyclotron motion in the this magnetron produce RF field, and this process of producing RF field continue until it hit to the cathode, hit back to the cathode, or hit to the anode. The third one is negative voltage magnetron. In this magnetron, there is no RF. RF is absent, and anode is divided into two parts. These two parts are isolated from each other. When this anode is at equipotentials, same potential is applied to the both sections of the anode, then electron performs cyclotron motion in this way, this way, this way, and this way. But if one side is biased, have a higher potential as compared to the other side, then equipotential trajectories are changed due to this biasing of anode. In this case, moreover, these biasing is alternating with RF frequency, or a frequency at which you want to produce the RF. And electrons are moving mostly in this region. When biasing is reversed, then they move in this region, this again in this region, and RF is cyclotron. RF is produced by the cyclotron motion of these electrons. These both are very low power devices. I mean, previous one, which is cyclotron frequency magnetron, and this one, which is negative voltage magnetron, have very low power devices, and their efficiency is very low. Then comes the traveling wave magnetrons. Initially, the traveling wave magnetrons were without RF structure around it. I like to say there were no RF cavities around it, as you can see here. It is the modern version of magnetrons, where you can see RF cavities here. So here, alternate voltage biasing was provided to these two segments of the anode, and the operation region was above the Hulse cutoff field. You can imagine that at Hulse cutoff, if the voltage is above the Hulse cutoff, what happens? Can anyone answer? No, first of my question. Then electrons will hit to the anode, and all the RF power, energy, potential energy will be converted into heat energy, a dissipation of energy. But here it is operated above the Hulse cutoff field, but the field is alternating. Means your voltage is alternating, which do not allow to hit, allow the electron to hit to the anode. G, please, your question. Yeah.
Was the structure the same? Also, voltage applied same.
Okay.
This one,
I try to explain. If you see here, negative, it's just like of this version was it's like of the negative voltage magnet. Here it has two segments. Again, one is negatively biased, other is positively biased. But in this one, biasing was there, but there is this one is with low voltage biasing, this was comparatively high voltage. Here again, you can see that anode has two sections. One is negatively biased, other is positively biased. And electrons interact with this field, additional field, which is between two separate anodes when they're passing. And biasing is operated such a way that when an electron is moving in this region, it gives the energy, because it interact with the field and give the energy in the form of RF. And again, when it comes here, this polarity have been changed and it produces RF again. In late 1939, Booth and Randall at University of Birmingham set about to combine the cylindrical anode magnetron work with Klestron's advantage of using resonators for confining the RF field. And they got comparatively high power magnetrons at that time, and those magnetrons were used in radars, and their efficiency was that they can evenly detect the submarine periscope at the distance of 7 miles. Then another development of oxide coated cathodes, which replaced the carbide theoretical tungsten cathodes, increased the power efficiency of these devices. And peak power of these devices were increased by an order. Now you can see the traveling wave magnetron, which is used nowadays. Its structure is like that one, as I have already explained that there is a cathode, electrons revolve here, and there are resonant cavities. In next slides, we shall discuss how these resonant cavities define the RF frequency. The primary difference between modern devices and previously we discussed the magnetron was modeled as 5J29 magnetron, is that it has these RF structures around it. And these RF structures consist of several resonant cavities similar to those which is an early version of pulsed cavity magnetrons. In this tube, the anode contains 8 resonators, and these are concentric with the oxide-coated cathodes. A permanent magnetic field can be used, or an electromagnetic field can also be used. The advantage of electromagnetic field is that you can operate at different parts, because you have to have a liberty to change the magnetic field, and your definitely anode voltage as well. Now, operation of traveling wave magnet, how we can explain the physics of these traveling wave magnetrons. When anode voltage is applied to the anodes and magnetic field is applied, and its filament is heated, electrons are emitted, and they revolve around the filament and form a space charge cloud around it, as you can see in the yellow disk. And these space charge cloud is termed as space charge hub. Generally, we can call it hub. And here, RF coupler is designed and connected, which RF produced inside is coupled to the outer source or outer cavity or any device where you want to use it. Now, how this work? Initially, when this hub starts, there is no RF inside this structure. What happens? The fluctuation in the emission, process, and noise amplify effects in the charge space hub. Electron velocities and charge density in the rotating space charge cloud fluctuate randomly. So there are components present in any of the frequency that may be supported by the cavities, structure, and magnetrons. Initially, there is a plethora of RF frequencies. Every RF frequency is present in the action of or operation of this magnetron starts. But only those frequencies survive which are resonant to these cavities. Other are suppressed. And this phenomena take a few nanoseconds, tens of the nanoseconds. And resonant frequency is set and it is operated at a particular frequency, RF frequency, and output is gained from this output coupler. But in simple structure, there are many issues which we will discuss shortly. Let's first discuss how hub is formed. R0 is the radius of the cylinder, inner cylinder, which has its outer surface, and this outer surface acts as a cathode which emits electrons. And when electrons are emitted, they perform cyclotron motion, so like this one, all around this periphery. Now, two forces are acting on these electrons. One is due to anode voltage, E field produced by anode voltage, EV. Second is due to the magnetic field, and it depends upon the velocity and charge as well. And it is the perpendicular to the motion of electrons or emission of electron, initial direction of emission of electrons. The path of electrons is approximately combining a low rotation around the cathode at radius R0 and a faster circulation motion with a small radius R0. Now, this radius R0 depends upon the initial kinetic energy of every electron, because every electron has different initial kinetic energy ranging from 2 to 3 or 4 or 5 EV. So it may vary different electron. With no RF, the maximum distance that an electron can move towards the anode is this R0, capital R0 plus small r0. And this is fixed by the ratio of electric field and magnetic field. In practice, generally it is half of the distance from cathode's outer surface to the anode's inner surface. Here the hub is moving, or space charge hub is moving. Now this space charge hub, as it moves around here under the influence of electric field and magnetic field, the velocities with which these electron stream move are given by this ratio, EY for the linear format, if you can consider a linear format, or EY for linear and ER for the circular format. We have a cylindrical coordinate of here of this electric field. Due to space charge, the electric field near the cathode is lower, because this space charge shields the electric field near the cathode, and the electrons near the anode see more electric field. So what happens then? Those which are near the cathode are their velocities are decreased. They are slipping. This flow is called slipping flow. The velocities of electron stream streams are of interest because the interaction with RF circuit in a magnetron, there must be near synchronism between the electron velocity and the phase velocity of the circuit. The top layer of space charge is assumed to be moving in near synchronism with an RF traveling wave on the anode. Then there is another limit. If the energy of electron is smaller than a particular energy, they fall back to the cathode. So we have to operate our magnetron between these limits. This limit is called Hartree line limit. Below this voltage, no field is amplified and magnetron stops working. As we have already discussed, that the electrons near this cathode have low energies, no kinetic energies, and outer have higher kinetic energies. And if applied voltage is less than a critical value, then these electrons which are moving around the cathode falls back to the cathode, hit to the cathode, and operation of magnetron suffers. Now there is another concept which is called spook. What is spook? We have seen that there is a cloud of electrons revolving around the cathode. When this cloud or an individual, first of all, we consider the individual behavior of an electron. A single electron leaving the cathode at point A here enter an accelerating field and is drive back into the cathode with appreciable energy, and it hit to the cathode and we produce the heat. But an electron living at the cathode at point B enter a deaccelerating field. When it's slowed down, it emits RF power of the same frequency as it is seen here. And it moves further ahead, interact with the field, and lose its energy in the form of RF power, and ultimately it hit to the anode. Now, again, we can see that the electric field pattern on the anode of magnetron is a standing wave that can be reduced into two waves of equal magnitude traveling in opposite direction. One wavelength of the traveling electric field pattern is shown, and an electron stream will either be adjusted so that it is moving in synchronous with traveling wave. The directions of forces on the electron opposite to the field direction are indicated at the bottom. Here you can see that the force acting on an electron moving around, their direction is as follows. Here it is this direction, here it is this side, it is upward direction, this, and this is reverse direction. These are forces when electron passes through the in front of the cavity. See the force of this kind, this varying force. For example, at point B, we can discuss the point A. Electron near A experience deceleration force because direction of force by this electric field is opposite to the motion of this electron. They move towards anode and RF field becomes stronger and electrons are pushed progressively into the spook, like projection that extend to the anode. Here it moves. When direction is opposite, it is pushed back to the spook because it is slowed down. Before further discussion, I want to show what is a spook. Initially, electrons are revolving here, then they interact with the RF field, and their shape is like this. This particular shape is called spook. When electrons move in this direction, electrons are here, just past the cavity, they are pushed back to the cathode due to those forces I have shown you in the previous slide. And when they move here, they are again moving towards the cavity, and this spook is circulating all around. And this spook is forming in every alternate cavity, in alternate cavities. In first, this one will be the spook, this will move, and now this cavity is empty, spook is moved here. And next, it is moved here, this part is moved here, this part is moved here, and this part is moved here, and so on. This spook is circulating. Now, these electrons which moves close to the cavity interact strongly with the field near the cavity, and they interact when this field produce RF. As shown here. Now similar concept is shown here. A spook is forming. Electron in the accelerating field region move through the spook from the cathode to anode. During synchronous interaction, electron at the surface of the hub and those transported to the anode move with a velocity approximately equal to that of traveling wave on the anode. The spook-like cloud rotate with an angular velocity such that it remains in synchronous with the alternating RF voltages on these segments. As the spooks pass the slot between anode segments, the RF field provide a focusing action that tend to further bunch the electrons. Now these electrons are bunched due to these cavities and form the spook. And these bunched electrons are more efficient to produce RF field. Now, little discussion about the spook as well. More discussion about the spook. An electron at position A, when there is a field inside this cavity, there is an you can see that there will be an electric field. When electrons moving in the spook are position A, what happened to them? Where the here the radial components of the RF field is in opposite to the DC field. The field applied in this direction. The radial component of this field is in opposite direction, and its angular velocity is reduced and it fall back into the spook. Now, spook extending up to the cavity is falling back. When this spook reaches to the other cavities, this point, what happens? Now, the field experience increased force towards the anode, and spook move closer to this opening of the cavity, re-entrant cavity, and interact with the field. Now, this same focusing action helped to maintain synchronism between the rotating spokes and the alternating field. The operating conditions of magnetron, magnetic field, voltage, and so forth are not as critical as they would appear to be at the first. Now, how the RF energy is extracted from this potential energy. The potential energy to an electron is provided by magnetic field and we have applied a node field, a node voltage. So these two fields provide the potential energy or kinetic energy to the electrons moving in the spook. And when these electrons interact with the RF field, they lose their kinetic energies and contribute to the RF power and increase the RF power. And this happens until the favorable conditions are changed and the particle hit back to the cathode or hit to the anode and produce heat. So now how the efficiency of a magnetron is calculated. The energy extracted from the power supply by an electron is the sum of its potential energy and kinetic energy. Since the kinetic energy remains nearly constant, it is the potential energy that is converted to RF power. In linear beam tube, the kinetic energy of the beam is converted to RF power and beam slows down as a result of energy exchange. But here in this scenario inside the magnetrons, the operating voltage of magnetron is typically several times the synchronous voltage. Ideally, the electron strikes the anode at the synchronous velocity, and so the anode dissipation is EV naught for each electron. Then the maximum theoretical electron efficiency can be defined by this equation. In practice, electrons follow cycloidal motion. They exchange many times the energy, and the efficiency of these electron is decreased, and the electron striking the anode with that velocity dissipate 4 times EV naught, as the electronic efficiency on average is this, where K can be 1 to 4. How many cycloidal motions it have performed before hitting to the anode or cathode. Now here is another issue that is called back bombardment. Many electrons are reflected back to the cathode. They hit the cathode and produce heat. Although we also producing heat to emit these electrons, but that heat produces by these back bombarding electron is much higher than our desire. Moreover, the kinetic energy and potential energy given to the electrons, instead of converting into RF energy, is converted into heat energy. So in a typical cross-field tubes, approximately 5 to 10% of the DC input power is dissipated in the form of heat to the cathode, heating to the cathode. In that scenario, the manufacturers give a voltage current graph which tells that at what voltage, what sort of heating you have to provide your filament to heat the cathode. For example, initially you have to heat the cathode with full required voltage and current. As you increase your average power of the magnetrons, back bombardment is started, and you have to reduce the heat to the heating you are providing from outside to the filament. And when this average input power of the magnetron reaches to this level, you totally shut down the heating of your cathode. The heating now is, yes.
But where the film is located, the cathode, by the cathode or outside?
No, it's a cylindrical, as I have shown in the first slide. Cylindrical, it is heated from the inside.
Heated from the inside.
Inside.
Okay, that's
And the bombardment on the outer surface also produces the heat. And when this heat is, bombardment heat is sufficient, you can cut off the supply which is heating the filament. All heating is required is produced by this back bombardment.
Sorry, I'm sorry. What's the material of the cathode? It's a metal cathode.
Which one?
The cathode material, what's it's because we have a secondary vision. I want to know the cathode material. It's a metal, copper or something.
I have already, it's coated oxides. Initially, they were ferrited tungsten.
Oxide of what material?
Barium oxide. There are a lot many. Kashif can explain better because he's much familiar with these materials.
I mean, can we use some kind of material with reducing secondary emission?
Here, I think secondary emission is not a problem. Your main purpose is to produce electrons.
I mean, because you said here is a problem. Because
Now, you are dissipating your kinetic and potential energy in the form of heat. That is the problem. And one way to reduce this problem is by a cut off your supply, which is heating independently to this cathode. So the main purpose is to produce electrons. It is produced by heating or by secondary emission are equally important. So here we can explain the RF circuit operation.
for you, can I add something?
Sure.
In fact, it is a blessing. Maybe you can go to the back side. See that if back bombardment is there, so you don't need to power up your filament because it is being heated up already. So you in fact reduce the power. It has to be measured, and that's why the company gives you the plot that high power. You don't need to heat up your filament yourself. Back bombardment is already doing the job.
But Kashif, bombardment is done to the cathode, not to the filament.
Yes, but because eventually filament is heating the cathode to emit the electron.
Secondary.
And if something electrons are back bombarding, they're also doing the same job.
Actually, filament is heating from the inside of the, to say this one. It is inside, isolated from the cathode. It is heating from the inside and back bombardment heating from the outside. Here, and here, where the electrons are striking to the cathode.
And the energy is bombarded is very low.
Oh, yeah. Now, RF circuit operation how can it be explained? Here is as I have shown, number of cavities around this filament. One of the cavity is shown. This part of the cavity act as a capacitor, and this part act as a inductor. And you can model this cavity by LC circuit. The resonant frequency of the magnetron is defined by these L and C. But keep in mind, when spook is passing through this slot here, as you have seen initially in the when spook passes near the slot or passes into the slot, definitely it changes its capacitance. And when you are designing, you must know how much current will be or charge will be in the spoke, how much perturbation will be produced, and what will be the effective frequency of this magnetron. Without this spook, the frequency will be different, but with the presence of the spook, the frequency will be different. We shall discuss the coming slides or differ. Okay, we were here. So the resonant frequency of the magnetron can be defined by this. The presence of electron I have discussed. The equivalent circuit of an 8-cavity resonator is shown, and the specified voltages and other parameters given by manufacturer when are deviated, the pulling and pushing effect of the frequency takes place. In spook, current can be increased, frequency will be changed because this capacitance will change. If it is decreased from those specific values, again the frequency will change. Sure.
Does the space charge affect the resonance frequency in this?
Yeah, space charge affect the resonance frequency because it affects the capacitance of this cavity. And the frequency is 1 over LC square root. Capacitance will decrease, frequency will increase. If capacitance is increased, frequency will decrease. But the frequency specified by manufacturer is for particular conditions, and it also gives you the specification. The voltage is, load voltage is decreased or increased, what shift of the frequency will happen, and what how the efficiency will be affected by this product. I shall discuss in detail in the coming slides.
The moment, the spook is unwanted action, isn't it?
No, spook is wanted action. Spook is wanted action.
Unwanted action.
You want to increase the space charge density by, like to say, bunching the electrons. You can see that
Get the microwave room, that's all.
now these electrons are not independently revolving as here. When the spooks formed, these electrons are bunched, and bunch electrons produce more RF field and efficiency is increased.
But they are entering into the cavity and changing the resonance frequency of it.
Yeah, sure. But when you are designing your magnetron, you have to design in such a way that you consider the amount of charge in the spook and effect of that spook on the capacitance of the cavity or even inductance of the cavity, and then you optimize your magnetron.
These are all tuning parameters.
Yeah,
These are all tuning parameters.
yeah, we will come to the tuning procedures and tuning parameters of tuning gadgets as well. So we were here. Okay, now discussing the RF operation. When we were considering the single cavity, there are a number of cavities, and the coupling of one cavity to other cavity is through the magnetic coupling. Here you can see capacitance, here you can see inductance, and these few lines are also passing to the nearby cavities, and so these cavities are coupled through this magnetic coupling to each other. In the desired mode of operation, sum of magnetic flux lines of each cavity link adjacent cavities. Now, the field in the adjacent cavity is 180 out of phase. When this happens, field in adjacent cavity is 1 degree out of phase. We call this mode of the structure a pi mode. We shall discuss in detail these modes and how they are calculated and what they are meaning and which one is more efficient for producing RF. And how mode jumping takes place and how we can deal with these modes. I think the next will be after tea.
Okay. Thank you, sir. And then we will continue.
Any question? We have few minutes.
Any question from them? Okay. And see you later in 15 minutes.